So we're going to actually move beyond planet Earth now and actually start thinking about other planets in our solar system. And we're going to start with Nathan Mayne from the University of Exeter, who's going to be talking about searching for an Exo-Gaia.
Thank you. So thanks to Kate for finishing with the image that I'm starting with, and also for reminding me when I was snorkeling many years ago and came pretty close to a basking shark, and that was pretty humbling for me, even though I just couldn't convince my Mark I brain that it wasn't going to eat me. So I feel like a bit of an imposter. I've never read the Gaia books. I didn't know much about the concept of Gaia until very recently. I've certainly never borrowed any swimming shorts from James Lovelock. My head has been trapped in a different sort of cloud. I'm an astrophysicist, and I've always been fascinated originally by stars. So more recently, I've tried to find a way of making what I'm thinking about and I'm working on more relevant, and I sort of found that, I think, in exoplanets. So what I'm going to talk about today is to try to talk about how I think, first of all, how we detect exoplanets, what we know about them, and then how it might help looking at the problem of an Earth system from a different angle, although I'm going to stop short of the 4F system, and R1 will follow behind after me. So there's Earth. Everything I show is not to scale. Most of what we're talking about over the last few days has either been about the Earth as a system or its evolution through time and what it might end up like in the near future or the further future. But there's another interesting question, which is, can we learn anything from comparative planetology? Can we look at different climates and understand? So to an astrophysicist, there are 3 planets in our system which are basically Earth-like. They're kind of the same size. They receive about the same budget of radiation to a factor of 2 or 3. When you do astrophysics, factors of 2 or 3 are fine. So the question that arises, and many people have been thinking about, is why are these 3 planets so different? Why is one 500 degrees C and rains sulfuric acid, and why is another one so cold? And one of the key parts of that story is probably the fact that life appeared here and has sort of regulated the system. But I'm not going to talk about the solar system planets. I want to jump even further out and talk about exoplanets, or planets we've discovered orbiting distant stars. Before I do that, I'm just going to slide in a little picture of Jupiter as imaged by the Juno mission recently, just to say that even planets without life are fantastically interesting. Okay, so exoplanets. We've discovered quite a few. They come in all shapes and sizes, and in fact, one of the key things we found very early on, just as science and physics in particular teaches you regularly, is the minute you think you understand something, a new piece of information presents itself to show you that you do not. And exoplanets certainly did that. I'm going to talk through a couple of the basic methods, and please approach me afterwards if this doesn't satisfy you and you want more information. But exoplanets have been detected really by 2 major methods, using either big, expensive telescopes in space, huge telescopes imaginatively named, like the Extremely Large Telescope, or even actually collections of small off-the-shelf cameras. The 2 main methods are really simple. This is the radial velocity method. You have a planet orbiting a star. The planet's gravity makes the star wobble, and you see this in the light shifting via the Doppler effect, just like a police siren driving towards you and driving away. The second method is even more simple. A planet moves in between us and the star, the light gets occulted, and we have a transit. And those 2 techniques are very complementary. One of them gives an idea of what the mass of the hidden planet is. The second one gives us an idea of what the radius is. So very quickly, we have quite a bit of information. We know how much stuff is in how much space. Is this a big puffy planet like Jupiter, or is it a terrestrial planet like potentially Earth? So we have transits, which give us a radius, and also an orbital period, which I didn't mention. We just see the transit regularly every 1 year for that planet. And a radial velocity, which gives us a mass. And again, that's a periodic signal every year. At the moment, our measurements are certainly optimal for planets in very short period orbits. They're orbiting several times in a year, for example, and that's because we can make repeat measurements. So many of the planets we're detecting are very close to their parent star for the moment. We also have other techniques where we can detect the emission directly from planets. This is a star in the middle that's sort of mottled by a coronagraph, just something to block out the light. And that is light coming directly from 3 planets, which are a bit like Jupiter in its younger, hot, angry days. As it was forming, a lot of that energy from the collapse is trying to escape, and they're very bright objects on their own. Another interesting technique is microlensing, where the light from a distant object is bent by the gravitational field of a planet. That's used to detect planets, but it's very hard to follow those up and find out any more detail about those particular ones. So that's great. We can detect planets, and we can say they're roughly this big, and they're roughly this radius. But we can go even further than that, actually. And one particularly interesting technique is transmission spectroscopy. Now, if we look at the transit, as the planet is moving in front of the star, it's blocking out light. If we change the wavelength at which we look at that transit, then we can see the size of the planet changing. Basically, the composition of the atmosphere is opaque to some wavelengths and then transparent to others. And this can give you an idea of the composition of that atmosphere. We've detected water, methane. The first detections were things like sodium and potassium because they're really big thumbprints. They were easy. But now we're detecting other molecules as well. It can also be a really easy way to detect things like clouds, as this light has to travel on a very long sort of path through the atmosphere. We can also detect from this emission from the planet, we can also kind of reconstruct what the temperature of the planet might be like. This is the wavelength of light, and this is how bright it is. And these are various models trying to fit to these observations. Now, for us, I live in a world where plus or minus 50 degrees C is fine. That's our accuracy level, which I know would be obviously catastrophic for a GCM of Earth. But this is early days, and we're starting to learn more and more about the temperature and compositions. The other thing we could do, two more things which I think are cool, we can look for these planets which are really close to the parent star. If this is the star, this is the planet. In this configuration, you're seeing the star and the day side of the planet. As it orbits around, you're now seeing the night side of the planet. So there's a change in brightness, very small, very subtle. But in this curve here, you see a slight change. Maybe you can't because of the light, but believe me, there's a slight change between here when the star is in front, planet is in front of the star, and here when it's behind. And that can give us an idea of temperature contrast between the day and night side, which are the kind of engine for the large-scale climate. Something even cooler is by looking really intensely for a long time, you can look at specific signatures of a given molecule. And this is time, and this is the wavelength. And you can see these lines have this really smooth structure. That's caused by the orbit shifting the signal from that molecule. We can flatten that signal out. We can remove the orbit. And actually, there's a residual left, which is the wind speed in the atmosphere of this planet. It's now been done 3 times for planets about 60 to 70 light years away. The measurements, an example would be 1.5 kilometers per second plus or minus a kilometer per second, so quite large uncertainties. But this is the first few times this technique has been done. And as the equipment becomes more suited to these measurements, we'll get more and more information. The reason that number is so large, by the way, is these planets are what's called hot Jupiters. They're very close to their parent star, and that drives really fast winds across the surface in the atmosphere, rather. We can even do this, and it has been done once. We can also even differentiate between hemispheres of the planets, measuring the wind speed as it comes into a transit and as it comes out. So we've measured wind speeds differently between different sides of the planet, and they agree, actually, with model predictions. So it gives us some confidence that what we're doing makes sense. So that's the kind of observations. What I do personally is I'm a theoretician, I guess. I'm a partnership. Well, I use the Met Office code. That can be incredibly painful and incredibly wonderful. But the reason I've done that is because I'm very committed to the hope that our study of planets and planetary boundaries from a different angle, by sharing software and people and knowledge, can in some way have some small impact on our understanding of Earth's climate, sort of coming at a question from a very different angle, which I think historically has proved useful. Now, we are trying to apply this model to a whole range of planets to learn more about them. And of course, one of the key questions is, do any of these planets host life? And you can break that, if you ignore a systems view for a moment, into a habitable zone or a region where perhaps planets could host liquid water and they might potentially host life. This is the distance from a star. The further away you get, the colder you get. This is the size of a star. The bigger the star, the hotter you are. And this region is a really simple calculation of where you might have liquid water with an exoplanet system, and then the three of the Earth-like planets in our solar system. But what we're finding, actually, is this is more complicated, especially in 3D. In 3 dimensions, you need to look at this problem more carefully. The second part of it, okay, this is just some stuff we've done. These are simulations of convection on these tiny lot planets. It behaves a bit differently. And these are plots of simulations of what clouds look like on these hot Jupiters. They're made of things like magnesium silicate, etc. And again, these match well with observations. It's not kind of made up. The second part of the question, which I'll leave to Arwen, and actually Jake Eager is going to be working with Tim and I and Andy this year on a PhD, is trying to look at how life affects this system in very simplistic terms for these exoplanets, and whether we might actually be able to detect them by finding different imbalances of gases in this transmission spectrum I was talking about, or other methods. One thing I want to really quickly finish with is visualizations. So one thing that exoplanets do is, I think, excite the public to a certain degree. We have these wonderful Art Deco posters of the Exoplanet Travel Bureau from NASA. And recently, we tried to do the same thing with some visualizations in 360 degrees. And we're taking this into schools to try to sort of engage young children in this. And we'll just quickly show you a couple of examples. This is WASP 121b. It's so close to its parent star, we know that it's evaporating. So we can see in the transit an asymmetric shape, and we've also detected various signatures. So we know it's got this cometary-like tail. Now, this is a 360-degree video. We can't do it here. Then to sort of get a bit more speculative, this is a simulation of what it might be like on a hot Jupiter. You have 1.5 kilometers wind speeds. It looks like we got lazy and used water clouds, but actually we know these clouds are highly reflective on this, scattering rather, on this particular planet. Sounds like a roving reporter in this. It's brilliant. And then the final one is a planet called 55 Cancri E, which is so close to its parent star, the entire surface is molten lava, we think. Okay, we'll leave those for a second. I think they could be useful in trying to help visualize climate solutions, to immerse people using augmented reality and 360 videos to try to help them visualize what we're trying to achieve. One thing I'm going to try and leave you with is to make you feel even smaller than kayaking on the sea. Here's a rough plot of exoplanets discovered. It's quite old, but basically there's about 4,000 now. We find them everywhere we look. We now think about 10 to 20% of stars like the Sun have a planet like the Earth orbiting them. So something about the same size as Earth that receives about the same amount of energy. Now, if we zoom out to our galaxy, there's about 300 billion stars in our galaxy, roughly, give or take a few billion. And about 60 billion of those are like the Sun, pretty much. So if you times that by the occurrence rate of Earth-like planets, we have 6 billion Earth-like planets potentially in our galaxy alone. Now, be careful, Earth-like doesn't mean they have universities and Facebook. It just means that they maybe have about the same radiation budget and maybe about the same size. So I'll leave you with the final image. This is about the size of the moon on the night sky, and in it there are 10,000 galaxies. So next time you're out of an evening, try to think how many moons you can fit around the sky, times that by 10,000, then times that by 6 billion. Quite a lot of potentially habitable real estate. But at the moment, the only planet we know of with any life at all is ours, so perhaps we ought to look after it. Thank you.
I'm going to allow one very quick question if anyone has one. Yeah, Colin. Where's Arwen?
Nathan, of course, the most Earth-like planet that we know is Venus. So when we talk about how many Earth-like planets there are, that gives a very, very misleading impression. It's something we've written on. So I'd like to challenge you, whenever you want to say Earth-like, perhaps you could say Venus-like instead.
Yeah, I agree. And secondly, I think I've learned that actually even when we think about Earth, probably the most likely configuration is a kind of Archean Earth, a sort of hazy yellow dot instead of a pale blue dot. So yes, I was being a little bit naughty. So I agree. Thank you.
Okay, cool. We're going to move on, I'm afraid, because we are still running late, but only just.